Welcome to today's Explainer. You know, it's so easy to just sit back on a train, look out the window, and marvel at the smooth ride. But right outside that window, engineers are fighting this hidden, massive battle against concrete and steel. We're talking about an incredible, almost entirely invisible friction between massive physical, civil structures and advanced railway technology. So today, we're going to explore exactly how the physical environment, the literal geography around us, shapes the safety, the speed, and the tech of the railways that we rely on every single day.
Right off the bat, think about this. What actually happens when a speeding train's communication is suddenly completely blocked by a mountain, or, say, a concrete tunnel, or a towering steel bridge? You see, the physical environment puts massive constraints on how trains navigate. We can have literally the most advanced signaling technology on the planet, but if a solid wall of rock is sitting between a train and its control center, well, we've got a major problem on our hands. So, to understand how we actually conquer these physical barriers, here is our spatial journey down the track for today. First, the infrastructure challenge. Then, bridges and viaducts. Next, navigating tight tunnels. And finally, the station interface. The infrastructure challenge and viaducts. Okay, let's dive right into this and look at our first major physical constraint, the built environment itself. You see, the built environment is just packed with friction. When engineers design those safe separation distances for trains, which we call headway, they aren't just doing math in a vacuum. They are fighting geography. Physical structures completely block a driver's line of sight. Limited physical clearances restrict where we can even place signaling equipment in the first place. Gradients, hills and slopes, dramatically alter braking physics because gravity is constantly pulling on the massive weight of that train. And, maybe most critically, the infrastructure itself severely limits our emergency evacuation routes. All these fundamental constraints force engineers to radically adapt where signals go and how they calculate headway. Take a look at this elevated viaduct right in the middle of a city. As beautiful as these structures are, bridges and viaducts can absolutely obliterate a driver's view of the signals ahead. The walls, the structural spans, the sweeping curves, they all create massive blind spots. And the reality is, if a driver can't see a signal at the absolute minimum required reading distance, they cannot safely react to it. So the crucial takeaway here is that we have to adapt to the viaduct, not the other way around. There's this very strict fundamental safety rule in railway engineering. It is highly preferable that trains do not stop on viaducts or bridges. Why? Because the risks associated with evacuating a packed passenger train suspended high up in the air are just extreme. Therefore, signals have to be incredibly carefully placed entirely clear of these structures so that absolutely no part of the train is left stranded on that viaduct if it's forced to stop. But here's the catch. When you shift that signal placement away from the viaduct, you directly alter the safe headway calculations and the braking distances for the entire line. The civil structure literally dictates the signaling math.
Section 2. Navigating tight tunnels. Now let's shift our journey from high in the sky to deep underground, because tunnels act as the ultimate stress test for railway technology.
Think about this. Above ground, communicating with a train usually just utilizes standard free space radio propagation. Simple enough, right? But underground, it is a totally different story. In tunnels with restricted clearances, especially the older ones without overhead electrification, the gap between the roof of the train and the tunnel ceiling is incredibly tight. In that tiny space, standard radio waves just do not propagate well at all. The physical mass of the train squeezing through the tunnel essentially acts like a giant plug, blocking the signal completely. Now, what's really interesting about this slide is how engineers overcome that blockage with a truly brilliant solution: leaky feeders. Instead of relying on a single antenna desperately trying to blast a radio wave down a curved tunnel, engineers run a radiating cable along the entire length of the tunnel wall. And this cable is intentionally designed to be, well, leaky. It has these engineered gaps or slots built right into its outer conductor. This actually unbalances the radio signal inside the cable and forces it to leak out, which propagates the radio frequencies consistently right next to the train, no matter where it's hiding in the tunnel. Look at how these intricate cable arrays are mounted directly along the tunnel walls. By using these leaky feeders, the communication system gets a totally predictable level of attenuation. The amazing part is that this signal strength isn't disrupted by a massive passing train squeezing through the tight space. It ensures the control center maintains a constant, unbroken stream of data with the train for vital safety instructions and automated operations. But listen, communication is really only half the battle of surviving the tunnel. Just like with viaducts, stopping a train inside a tunnel is absolutely terrifying and incredibly dangerous.
There's this severe risk of toxic fumes building up, and getting passengers out in an emergency? Absolute nightmare. So, whenever practically possible, signals are pushed outside to avoid trapping a train in the dark. But when signals absolutely must go inside, the limited clearance of the train pushing through means we need specialized, bespoke, much smaller tunnel signals. On top of that, curved tunnel walls completely destroy the minimum reading distance for the driver. And if that wasn't enough, bright sunlight at a tunnel exit can completely wash out a signal's lights. It's like the tunnel fights the signaling system at every single turn.
Section 3, the station interface. Let's move to and see how this builds up to our final destination, the busy passenger station. The station is where heavy, fast-moving machinery directly collides with high passenger densities and totally unpredictable passenger movement. It is a highly volatile interface. One of the craziest dangers here happens if a passenger train is stopped at a signal and only a portion of the train is actually sitting within the station platform. Confused passengers might try to board or even jump out of doors that aren't actually over the platform. Also, just look at the curves, the platform furniture, the overhead canopies. A crowded platform, packed with this much visual noise, can completely blind a driver to the signal ahead.
So, to mitigate those massive hazards and actually see past the canopies and platform furniture, engineers might have to install extra signals on the approach or even midway down the platform. This gives the driver an early heads-up of the next aspect, right over the heads of the crowd. Furthermore, the sheer proximity of the platform itself makes installing and inspecting trackside equipment really dangerous. Because of that, train detection equipment and junction boxes are deliberately pushed clear of the platforms. This creates dedicated safe zones so maintenance staff can actually do their jobs without being in the line of fire.
Section 4, automated platform doors. Now we're transitioning into the most complex station interface, how fully automated systems interact directly with physical structural barriers. And this brilliantly illustrates a modern solution to this whole problem: platform screen doors, or PSDs. In high-capacity mass transit systems, especially the ones using moving block automated train control, the passenger densities are just astronomical. The PSD system physically isolates that dangerous track environment from the crowded platform. Yes, it's a massive piece of civil infrastructure, but it is entirely commanded by the invisible signaling technology running the show behind the scenes. Let's actually walk through this critical automation sequence step by step to see how the signaling system directly commands the physical infrastructure. First, the automated train has to dock at the exact, precise, correct position along the platform. Second, the signaling control systems verify this exact alignment. Third, a perfectly synchronized command is sent so that both the train doors and the physical platform doors open at the exact same time. Finally, the doors close. But here's the magic. If a bag or a person obstructs that platform door from closing, the interlocking system detects this and instantly, literally instantly, prevents the train from being given any movement authority. The physical infrastructure and the digital signaling are just flawlessly synchronized. We've seen how elevated viaducts alter braking math, how those genius leaky cables conquer pitch-black tunnels, and how automated doors protect our bustling stations from unpredictable passenger movement. The built environment isn't just a backdrop for our commute. It is an active, challenging participant in how we engineer safe travel. So, I'll leave you with this provocative thought. As trains become faster, more frequent, and fully automated, what unseen constraints in our ever-growing urban infrastructure will engineers have to conquer next? Think about that. The next time you commute, look out the window. You might just see the incredible, invisible engineering holding the whole shebang together. Thank you for joining me on this explainer, and keep your eyes open to the fascinating